I had to pause the video for a second. My dog was barking, so I offered to give him a bath, and he is no longer barking. So, okay, so back to this. Ethane, 2 carbons. For the ethane is a single bond, and then we add enough hydrogens on the outside. Let's move on. Let's make it a little crazier. Let's go ethyne. Okay. So if I were doing an ethyne, again, the eth tells me that there's 2 carbons, so a carbon and a carbon. But the yne tells me that they're triple bonded. Boom, boom, boom. Cool? So now you think, okay, each carbon again needs to have 4 bonds. So currently this carbon has 1, 2, 3, so it needs 1 more. So you just put 1 hydrogen on it. Same thing with this one. This carbon has 1, 2, 3, needs 1 more. Boom, you put 1 hydrogen. Each carbon now has 4 bonds. Okay, let's do a couple more, just to make sure we're feeling good about this. Let's say we're going to do pentane. Pent over here tells me that there's 5 carbons, like a pentagon. So we have a carbon, 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 carbon. Cool. And then the ane part tells me that they're single bonded. Single, 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 single. Cool. And now you just add the appropriate number of hydrogens to make sure every single carbon has 4 bonds. So this carbon currently has 1, so it needs 3. The same thing with this other outside one. It currently has 1, it needs 3. But then every other carbon that's in between already has 2, so it only needs 2 more to have 4. And that's pentane. All right. Now that we're feeling okay so far, hopefully, I'm going to introduce something else, and it's called skeletal structures. Skeletal structures are what we're going to be using for the vast majority of OChem. And what skeletal structures do is, because carbon is so important, you assume a carbon and all of its hydrogens at every point, like every vertice and end. That might not make any sense, but let me give you an example. Okay. Believe it or not, what I just drew here is pentane. Let's talk about how. At every point and end, there's a carbon and its associated number of hydrogens. So there's 1 right here, there's 1 here, there's 1 here, here, and here. So 1, 2, 3, 4, 5. The lines between them represent the bonds. So all of these are single bonded, carbon to carbon, single bond, single, single, single. If it had been a double bond, I would have drawn 2 there, for example. Okay, and then again, it represents its respective number of hydrogens. So this carbon has 1, 2, 3 hydrogens, this carbon has 1, 2, etc. So this would be the skeletal structure for this. Now, oftentimes you can take a skeletal structure, especially when you're first getting started, and just draw, like, okay, like that's a carbon, that's a carbon, that's a carbon, that's a carbon, that's a carbon. Draw the actual structure on there, and that will help you kind of get used to things. But I'm going to do it now so that we can ensure that you see it's the same as what's up here. Yes, it's turny and wavy, and I could have drawn this pentane just as turny and wavy if I'd wanted to. We'll talk about shape here in a little bit. All these carbons are going to be tetrahedral shape. But hopefully you agree there's carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. It's the exact same molecule. So boom, 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 boom. That's the way I would draw pentane, and it's going to really help if you start trying to see the skeletal structure as what we would have used to call the Lewis-Dot structure. Okay, going over to here to ethane and ethene, a little bit harder on these because there's only 2 carbons, but ethane would have just been a line, and ethyne would have been 3 lines like that to represent it. So again, at every end, there's a carbon, and here there's a carbon with associated hydrogens. Okay, let's move it up a notch. let's go ahead and say we want to do butane. Okay. So but is over here, it's 4. So we're looking at something with 4 carbons. Carbon, 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 carbon. And the ine is telling us that it's triple bonded, right? But if you draw a triple bond in all of these, you'll very quickly realize carbon only wants 4 bonds, right? So how can this carbon have 6 bonds? It actually can't. That can't happen. So carbon can only have 4 bonds. So this thing doesn't actually work. However, you can name where you want the triple bond in terms of numbers. So we can number the carbons. So let's say I number this carbon 1, 2, 3, and 4 for the 4 carbons. And then I say which number I want that triple bond to be after. So let's say I say but 1 ine. Then after the first carbon, there will be a triple bond. And all the rest are assumed single unless the molecule says otherwise. And from there, we can add the respective hydrogens. This carbon has 3 bonds, it only needs 1. This carbon already has all 4 bonds, it needs no hydrogens. This one needs 2, and this one needs 3. Okay. And this would be but 1 ine. If I were drawing this in a skeletal structure, I would draw it like this. 1, 2, 3, 4 carbons. And we'll talk about why it's straight. But if for now you drew it something like this, 1, 2, 3, and then boom, boom, boom. In fact, let me go ahead and color these in to make it a little prettier. I grabbed whatever color stuff I could find. I have a blue pen, a green marker, and an orange crayon, but hopefully that works. So let's say this is that carbon is right there, okay? And if the green is this carbon, that one's right there. And if the blue is this carbon, then it's right here, okay? And then the brown is this carbon, it's right here, okay? So this and this are equivalent. So but 1 ine would be that. Let's go ahead and counteract that, and feel free, if that didn't make sense, pause it, watch it again, and usually that will help. Let's say I wanted to draw but 2 ine, just to keep everything else consistent, but change one little thing. The but tells me that there's 4 carbons. Carbon, 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 carbon. The ine tells me that's going to be a triple bond, and the 2 tells me where that triple bond is going to be. So if I number these 1, 2, 3, 4, then that triple bond comes after the 2 carbon. Okay. The other ones are assumed single, like that. And then I add the appropriate number of hydrogens. 1, 2, 3 on this one, so this carbon has 4 bonds. On this one, it already has all 4 bonds. This one already has all 4 bonds, and this one just needs 3 more, and that sucker's done. So if I were to do a line structure of this, I would go, okay, this would represent that. Again, let's pull out the color marker system, color marker crayon pen system. If that's that carbon, I'm talking about this one right there. Okay. And if this is number 2 carbon, that's that one right there. If this is number 3 carbon, that's this one right there. And if this is number 4 carbon, that's that one right there. All in a line. And if you had drawn it like this for now, I would not have freaked out. This, however, is the appropriate way to draw it, and we'll talk about why here in a bit. Well, actually, I'll tell you right now, these are going to be in a line all the time. Anytime you have a triple bond, it's a line. But we'll talk about shape here. and the Y. Okay, so for now, hopefully we're getting a decent idea of how these things work. Let's go ahead and move on. See what's coming up next. Okay, so here we're taking our skeletal structures and putting them into fluid dot structures, and vice versa. So only carbons are invisible, right? So only the carbons have these points and turns. Otherwise, if you have something like an oxygen, like we have down here, you actually draw it over here on your left. You'll actually want to draw the oxygen itself in there. You don't want to just put a turn or something like that. So only carbons are special, and hydrogens, I guess. So when I go to do this, when I'm first starting off, again, one of the suggestions I make is to just put a carbon at every corner and vertices you have, okay? And then draw the associated number of hydrogens. And that will be correct. This one, I almost put 2 on this, but I have to be careful. It's got 1, 2, 3, 4 bonds on it already, so it only has 1 hydrogen. Okay. So this would be its Lewis structure, believe it or not, but I could draw its Lewis structure here if I want to. You could do it in a line, or you could do it the way we just did it. Carbon, 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 carbon. So I'm just redrawing it just to show you that it's the exact same thing. So only the triple bonds are drawn in the line. Double bonds can be drawn at angles as well. So this would be its Lewis structure. All right, same thing over here. It looks kind of funky, right? But every corner is a carbon. So, so let's go ahead and put a carbon, 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 carbon. And if we put the associated number of hydrogens, we'll have the Lewis structure. Cool. But I'm just going to go ahead and draw it over here just to make sure you've got that carbon, carbon, single bonded, another carbon, another carbon. You'll be drawing lots of hexagons in organic chemistry. Let's go ahead and just get used to them. Okay. So this is what it would look like, and now we just need to add the hydrogens. So this one would have 2. Actually, all of these would have 2. Except for these guys right here, which already have 3, so it just needs 1 more hydrogen. Same thing with this one. You could put the hydrogen anywhere. You could have put it down here, you put it up there, you put it up there. And this carbon over here, these end ones are going to have 3. So now every carbon has 4 bonds. So this is representative of the original one before I drew all the carbons on here. Okay, if I were in class, I'd say, do you have any questions? But we're not. So if you have questions, come talk to me. All right, let's move on to this one. So when it comes to something like this, and I'm representing it in a line or vice versa, or some kind of complex thing that looks a little scary to me, I find a starting point somewhere in the middle, and then I do everything to the right, and I do everything to the left, and it helps me a lot. So I'm going to start with this oxygen right here. Off of this oxygen, there are 1, 2, 3 carbons, right? So this oxygen is bonded to a carbon, and then I'm going to go 2, so that's 1, 2, 3. Okay, you could have gone up, down, up. There's lots of beautiful ways you can draw this, and that's kind of the fun part about organic is you can mess it up a lot. But there's 1 carbon here. Maybe I should have made it a little crazier. 1 carbon there, that's that one. A carbon here, that's that one. And a carbon at the end here, that's that one. And now this carbon at the end is attached to an oxygen and a hydrogen. Now, if you remember, I said anything, so oxygen to a hydrogen. Anytime you have an oxygen, you actually have to draw it, and even if it's attached to a hydrogen. The only time hydrogens are invisible is when they're on carbons. So we drew this first half on the right. Now we're going to go on to the left. Hopefully you agree this oxygen is attached to a carbon, and that carbon has 2 other carbons like splitting off from it. So let's go ahead and draw that. This oxygen is attached to I'm going to draw it down. I could have drawn it up and drawn it straight. This oxygen is attached to a carbon. That's this one. and that carbon is attached to 2 other carbons. Okay. So I'm going to go ahead and do that in color. Well, this one's already blue, so let's keep it blue. This carbon right here would be this one right in the middle, okay? And then that one is that one. And this carbon down here is that one right there. And this would be our final product. Now, you do not necessarily have to draw the dots in these skeletal structures. You can if you want to. You can put them wherever you want to, but you don't have to. They're not required. But they will help you in the future if you start getting used to drawing a specific number of dots. And that's part of today's lecture too. So, all right, last but not least, let's move on to this one. This one looks pretty cool because I don't know about you, but I see like a square in here. I see the 4 carbons. I'm gonna start with that square. Boom, that knocked out 1, 2, 3, 4. Now we just need to go to each individual carbon and ask what's attached to it. So let's start with this first one. This carbon is this upper left-hand corner one. And hopefully you agree it has an associate number of hydrogen on it, which it should. We don't need to draw those. And it has another carbon over here. We only draw the carbons. So, boop. This CH3 right here is this dot right there. Okay. So we took care of this one. Let's move on to the right over here. Here we have a carbon, that's that one, and it's attached to 2 carbons and then a chlorine. So what we want to do is have 2 turns or ends and then a chlorine. So that's the first end, that's the second end, and then a chlorine. Okay, and it does definitely take some getting used to, but that is this one. Okay, the green is that one, the blue is going to be this one, and then there's a chlorine. Again, you don't have to draw the dots on a chlorine, but if you did, you should know that there's 6, and if you don't know that, that's okay, because we'll talk about it here in a little bit in the lecture. This carbon, do we have to draw anything on it? Hopefully you agree not, because there's no carbons attached to it. It's just its associated hydrogen, so it's already built into that corner right there. And then last but not least, this one. Do we have to draw the nitrogen? Hopefully you agree the answer is yes, because only carbons are invisible in the skeletal structure. We have to draw every other one, so every other element. So this carbon is attached to a nitrogen and 2 hydrogens. So what you can do is you can just write a nitrogen and it's 2 hydrogens, okay? And this would be the skeletal structure of that. So if you found the markers to be helpful, I suggest getting some colored markers or pens or crayons or a combo. All right, crew. One thing I could do real quick is go back up to this one, just to reiterate and remind you of what we've already learned. So I'm gonna redraw it real quick here. Let's see. Run out of paper. So I'm going to redraw this one. All right, so those are all old notes. So we had something that looked like this, boom, 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 right? Now, these are 3-dimensional structures. So hopefully you agree that this is the same as this, right? It can turn around. So if I asked you to name this, these are equivalent. Exact same thing. Again, you took this thing and you flipped it over and you would get this. If I asked you to name this, you would hopefully agree it's got 1, 2, 3, 4, 5 carbons. So it's a pent of some sort. Then you see it's got a double bond. So it's a pentene of some sort, right? The only thing is you can't just call it a pentene because that assumes that there's double bonds everywhere, right? We're going to have to label where the double bond is. So is it going to be 1, 2, 3, 4, 5? Is it going to be pent 3-ene or is it going to be pent 2-ene? It's going to be pent 2-ene because you always want the lowest number. So if I were to give you this structure again, the way it was originally drawn on the paper, to remind you, I'm just copying what was here. If I were to do it this way, you always want to start the numbering from the side. Start numbers from side with closest point of difference. So you're going to start the number from the side with the closest point of difference. Okay? So that would be this side, because if I start this way, I got to go 1, 2, 3 before I get to this double bond. Here I only have to go 1, 2 before I get to the double bond. 1, 2, 3, 4, 5. And again, that's why it was pent 2 ene. So just to remind you of some nomenclature, because it's been a minute since we talked about it. All right, funsies. The rest of it, I don't expect you to be able to do yet. Don't worry. Ooh! New structures. Okay, formal charges. Now, right now it would be very handy if I had a periodic table, but I don't, so bear with me. I'm going to draw one. Let's go over formal charges. Formal charges, valence minus sticks minus dots. Everything we've drawn so far has been neutral in terms of formal charges. And on in your modules or on pages, you will have a video going over formal charges from like Gen Chem 2. However, or Gen Chem 1 actually. However, we can make it a lot simpler, I think. So just to remind you of a periodic table, looks something like this. Okay, and there's right here is carbon, nitrogen, oxygen, fluorine, a bunch of the noble gases we don't really care about because they don't bond. We also have boron, and then lithium, beryllium, pretty much. Cool. So 1, 2, 3, 4, 5, 6, 7, and 8. And we call those columns. Columns 1, 2, 3, 4, 5, 6, 7, and 8 because we're brilliant. Okay. Some people call them group 1A, stuff like that, but that's too fancy for me. So 1 through 8 is what we got. Now, if you remember, everything wants to be like a noble gas. It wants to have 8 things. So carbon right here currently has 4 these are also they're the column numbers, but they're also the number of valence electrons, the electrons that can do chemistry. So carbon has 4 valence electrons right now. It wants 8. So how many does it need to have in order to get to 8? Well, if it has 4 and it wants 8, it needs 4 more, right? And that is why carbon, when it's at its happiest, has 4 bonds. Okay. Let's look at nitrogen. Nitrogen has 5. How many does it need to get to 8? It needs 3, right? So nitrogen makes 3 bonds. However, you should memorize that nitrogen makes 3 bonds, but it also has a lone pair of electrons. This is just memorize these suckers. Oxygen is right here. It has 6, so it wants 2 bonds to get to 8, right? And therefore, boom, 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 it takes on 2 bonds, and it has 4 dots on it. Okay. The dots are so that A, it follows the octet rule, but B, also that's how you need to get to its formal how you need to figure out its formal charge. So let me go through formal charge real quick, just to show you that these are all zeros. When 0 formal charge. So formal charge equals the number of valence electrons minus the sticks minus dots. Okay, very fancy. So looking at this carbon, if I asked you the formal charge on the carbon right now, hopefully you agree carbon has 4 valence electrons. So its formal charge equals 4 valence electrons minus the number of sticks touching it, 1, 2, 3, 4. It needs 0 dots in order to have a formal charge of 0. And that's why carbon looks like this. Let's look at nitrogen. Nitrogen's formal charge equals the number of valence electron nitrogen has, which is 5, minus the 3 sticks touching it, 1, 2, 3, minus how many dots does it need to get to 0? Hopefully you agree it needs 2 dots, and that's why it has 2 dots. Then we look at oxygen down here. oxygen, in order for it to have a 0 formal charge, we look at the fact that it has 6 valence electrons. It currently has 2 sticks touching it, and that's how it gets to 8 valence electrons. So it has 2 sticks touching it, minus how many dots would it need to be 0? Hopefully you agree, 4, and that's why we have 1, 2, 3, 4. So you can use formal charge to figure out how many dots you need on anything. Okay, so all of these are like standard states where you generally have carbon, nitrogen, and oxygen, and you don't have to write any charges if they're like this. So everything we've worked with thus far today has things that have these charges. Just to prove it to you, I'm going to go back here and show you. Oxygen here, for example, had 2 sticks and 4 dots. Remember, when oxygen has 2 sticks and 4 dots, its formal charge is 0. Therefore, we didn't have to write anything. Nitrogen, we didn't even draw a diddly squat, right? But you did know it's got 1 bond there to the carbon, and it has 2 hydrogens telling you there's 3 bonds. If it's got 3 bonds, it's going to have 2 dots to equal 0. Right? So even though you didn't draw the dots, you should know the dots on that nitrogen exist. All right. So what if it's not 0? What if we're talking about something that has a charge? Well, in those situations, you actually have to draw the charge in or write the charge. You can't just assume that we know. But I just kind of gave you some things to memorize. When oxygen has 3 bonds, it's going to have a +1 formal charge. Okay, let me give you an example. I should have put, it also has 1 lone pair. 1 lone pair. Okay. We know when it has 2 bonds, it's going to be 0, right? And if it has 1 bond, it's going to be a -1. This one is probably the most important one you need, but let me show you why. So let's say we have an oxygen with 3 bonds. So you've got something like this, and it's got 3 things on it. Okay. It would, even though there's no lone pair written, we would assume a lone pair. And it's just something that you're going to want to start memorizing. So if we looked at the formal charge of this, we know oxygen has 6 valence electrons. It has 3 sticks touching it. It has 2 dots. And therefore, its formal charge is +1. Okay? So anytime you see an oxygen with 3 bonds, it automatically has a +1 formal charge. You might actually want to write that plus on there to remind yourself it's got a +1 formal charge. Then the really important one is this. Again, let me do one in the middle. We already said if an oxygen has 2 bonds, it has 2 dots, and its formal charge is 0, right? But if we have an oxygen that's just a single bond, just a single bond, it's going to have 3 lone pairs on it. And its formal charge is going to be -1. Again, that's because the number of valence electrons is 6. It has 1 stick touching it. And it has 6 dots, giving us a -1 formal charge. So every time you see a single bonded oxygen, it automatically is a -1 formal charge. You don't even have to write the -1. You could have just written a negative on there, okay? Like that. There's some others we'll occasionally run into. Nitrogen with 4 bonds is always going to be a +1 formal charge. But these are the big ones. This especially is the biggest one. Oxygen has 2 lines on it, dude's 0. Oxygen has 1 line on it, dude's -1. Okay? Even if those dots aren't written, because again, in skeletal structures, you don't have to have a dot. Carbon, you can see, it can have 3 bonds and be +1, like this. Or it can have 3 bonds and be a -1 if it has a lone pair on it, like that. And you can do valence minus sticks minus dots. Because that's confusing, when it comes to carbon, you'll always have somebody either write a plus on there or write a lone pair on there. There will be something to indicate which one is which, because you can't just leave it like that or you would not know what you're doing, right? So when it comes to carbon, it's confusing. It will always be given. Everything else, if nitrogen's got 4 bonds, it's +1. If oxygen has 1 bond, what is it? It's got to be -1. Okay. So let's go ahead and practice that here. say in every element but H, but I also mean carbon. Because again, carbon, if carbon's a negative, it will be given to you. So let's start with this one right here. This oxygen, it's got 2 bonds, right? If it's got 2 bonds, its formal charge is what? Hopefully you agree, 0. You could draw the dots on there if you want to. It's not gonna hurt you and probably will help you in the future, but it's 0. I wanna look at this other oxygen. How many bonds does it have? Just 1, so hopefully you agree. Boom, 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 boom. This sucker's a negative formal charge. Okay, this is really important. When you recognize single bonded oxygens must have a negative charge. Nitrogen with 3 bonds, if you remember, is always going to be 0. They also all have a lone pair on them. Even though that lone pair isn't drawn, we could draw it. So all these nitrogens have a formal charge of 0. You don't have to write the 0, but I'm doing it just for a point. However, this nitrogen right here has 1, 2, 3, 4 bonds. 4 bonded oxygen has what formal charge? Hopefully you agree. It's a positive formal charge. It's one of those I'm going to ask you to memorize. Okay, these right here are the most common situations you'll find. A positive nitrogen, a negative oxygen. So just get used to it. Nitrogen with 4 bonds must be positive 1. Oxygen with 1 bond must be negative. All right, moving on to this one. Again, this carbon right here, my software wouldn't even let me just put a carbon here. It's like, no. You have to have a carbon negative because again, it will be given to you. So this carbon with negative charge tells you that there must be a lone pair on that carbon, if you remember. If you didn't know this, if you didn't know that there was going to be a lone pair, how would you figure it out? Well, you'd say, okay, what's the formal charge? The formal charge is negative because it's telling us it's negative. We know that formal charge equals valence minus sticks minus dots. Carbon has 4 valence electrons. It currently, in this situation, has 3 sticks touching it. So how many dots does it need in order to be a -1? It has to have 2 dots on it. And that's how you know you draw 2 dots. All right, moving on to this oxygen right here. Oxygen has 1 bond. What's its formal charge? Hopefully you agree, -1. All right, this oxygen has 2 bonds. Boom, we like that. We're used to those are 0. This nitrogen has 3 bonds. We like that. We're used to that. That's 0. This nitrogen has 4 bonds. We're like, we know that's different. What's its formal charge? Positive. All right. So hopefully that made some sense. If it didn't, again, go back, watch it again. Look at the chart that I provided you, or the list of the different formal charges. Okie dokie. We're moving on. Okay. Bond strength and length. Okay, before I get here, let's see, before I get here, we are going to introduce why I drew stuff with triple bonds as a line, and why I drew stuff with double bonds and single bonds as not a line. So, if, for example, you have, well, let me do this. I should do these in order. Redo. Okay. So carbon with 4 things on it. Carbon, 2 things, carbon. Okay, these are the situations you'll most often encounter. A carbon with 4 single bonds on it, a carbon with a double bond on it, and a carbon with a triple bond on it, okay? So ignore this down here. Boom. Ignore what? You don't even see it anymore. Okay. So if something has 4 things on it, 4 electron groups on it, these are called electron groups. Even a double bond is an electron group and a triple bond is an electron group. Electron groups are anything is a lone pair, a single bond, a double bond, or a triple bond. Those are called electron groups. So how I like to picture this and how I talk about it in classes, I picture these as like each electron group as a sibling, right? And if siblings are trying to get away from each other as far as possible. So let's say you're driving in a car and you got four kids that are fighting. You pull over and you take the kids out and you want to get them as far away from each other as possible. What you do, if each end of my pen is 1, there's one kid there, there's one kid there. Okay, so I'm going to draw it up, like stand it up like this. There's one kid, there's one kid. So you stand on one kid here, you stand on one kid here, you lift the other two up, and you point them away like this. This is, right here, as far away from each other as you can get, okay? We call this tetrahedral. So this shape is called tetrahedral. And I should have a video you can watch on geometry. That's an optional video. So they're tetrahedral in shape. They're 109 degrees, 109.5 specifically, apart from each other, okay? So it's like a little X, but a twisted X. All right, let's look at this one. Here, so again, we had 4 electron groups. Here we have 3 electron groups. In other words, you've got 3 siblings that are fighting and you're trying to get away from each other as far as possible. Well, in that situation, if this is one sibling, and this is one sibling, and this is one sibling, all you gotta do is hold them like this, as far away from each other as possible. So maybe you step on one, you step on another, and lift the other one high up into the air like this. Oh, I lost. I killed one of them, no. Okay, something like this, okay? That's called trigonal planar because it looks like a triangle, right? And it's all in one plane, so trigonal planar. That's 120 degrees. Okay. And last but not least, if you have 2 siblings that are fighting and you want to get them as far away from each other as possible, you don't have any bend, right? You're not like that. You're not like that. You're as far away from each other as possible in a line. That keeps them as far away from each other as possible. And that, because there's 2, and that is called linear because it really does form a line, right? And that's why when you draw carbons with triple bonds, everything must be in a line. This is 180 degrees. You know a line is that. So going back to when we drew, like when we had a carbon, triple bond it to a carbon, to a carbon, to a carbon, to a carbon, right? Let's go crazy. Whoops, why am I drawing a hydrogen on that? I don't know. You should yell at me. Okay, so I got 1, 2, 3, 4, 5 things. Okay, so this would be pent. On the very first carbon, I have an ine. So pent, 1 ine would be drawn like this. This would be the end, so that would be the carbon. Oops. Wait, let me redo this. This would be the end, so this would be the carbon. So I'm going to draw the triple bond here, so that this carbon right here is that sucker right there. This carbon right here is that sucker right there. And again, it's keeping this one as far away from each other as possible. So that's why this next carbon has to be a line, okay? So this over here and that over there have to be in a line. And then from there, you're back onto something with 4 on it. You're back into tetrahedral territory, which is why you can then bend around, okay? So blue here, green there. Let's go orange here, okay? Brown here, and then black is that one. Cool? So that's why we had to draw it in a line. Now, if really any time in this class, if you end up drawing it like this, because there are times when this stuff gets really hard and you do that, that's okay. I won't freak out about it, okay? But this is ultimately the correct way to do it. So sometimes I'll draw it like this, and then I'll remember, oh, this has to be in a line because it's linear. So then I'll draw it like that, okay? All right. The other thing we have to talk about is hybridization. So sometimes hybridization is covered in Gen Chem 1 and sometimes it's not. If you had me, it definitely was, but it's not so bad, I promise. So if you remember, when you were talking about electron configuration way back in the day, you talked about S, P's, and D's. Well, there was 1 S, there were 3 P's, and there were 5 D's. Okay. all you do to figure out hybridization is look how many groups are around something and then figure out how many letters that is equivalent to. So this carbon has 1, 2, 3, 4 groups, right? So you go through 1, 2, 3, 4 letters. An S, a P, and a P. So its hybridization, we would say, is SP3. Cool? Because you went through 3 Ps. Let's look at trigonal planar. There's 1, 2, 3 things. So you go through 1, 2, 3. You went through an S and 2 Ps, right? So we would call this SP2, hybridization. And last but not least, linear. There's only 2 things, just an S and a P. So we just call it SP. If you put SP1, I wouldn't freak out, but SP is the appropriate way because chemists don't like the number 1. So, all right, these are pretty much the main ones you have to know. You absolutely have to know these. So when I say an sp3 carbon, you're like, boom, I know it's a carbon with 4 things on it. If I say an sp hydrogen or an sp carbon, you're like, boom, I know it's a carbon with a triple bond and a single bond. It's got to be linear. So these, definitely know them. I'm hesitant to say memorize because you really shouldn't have to memorize. You should understand the concept. The only thing you have to memorize is pretty much the name tetrahedral because that's just weird. And the bond angle 109.5, that's just weird. Everything else should hopefully fall into line and make a lot of sense. All right. So with that out of the way, let us continue. Bonds are strong when length ain't long. I don't know what I was smoking when I wrote that. But what was really funny, I thought this was really stupid, but then somebody wrote to me and said that it helped them on their MCAT for some reason. So I said, okay, cool, I'll keep it. All right, bonds are strong when length ain't long. So I do this demo in class, but if you've ever played Red Rover, that's you and that's somebody else. Red Rover is essentially this. You hold hands with somebody, and then somebody else tries to break through you, right? Okay, so if you're holding hands, just one hand like that, they can usually break through you, okay? It's not so bad. So this would be like representative of a single bond. Single bonds tend to be weaker, okay? If those two face each other and they hold 2 hands, like this, okay? This would be representative of a double bond. And I should have drawn them a little closer, but when you're holding 2 hands, your bodies are actually closer together. So not only was this single, this was far apart. This represents a double bond. It's moderate in strength. And its distance is moderate as well. Now let's say you're standing there facing each other and you've got 2 arms and then you're like, let's link legs. For anybody who has seen this demo in class, it's kind of goofy. Okay, so they're holding hands and they're linking legs at the same time. This would be representative of a triple bond. Its strength is strong. It's much stronger. And its distance is close. Okay, so the shorter the distance, the stronger they are. And triple bonds are the strongest in terms of the distance, and single bonds are the weakest because they're far apart. Okay, so it's easier to break something that's all stretchy and long. Okay, so we also should recognize that something with a single bond, like if each person is a carbon, these would both be sp3 carbons. Okay, they each have 4 things on them. If we have a carbon double bonded to a carbon like this, that these would both be sp2 hybridized carbons. Okay. And we should recognize this one. That sucker would be a line, right? And this would be sp. These would be sp carbons. Each of them would be called sp hybridized carbons. Okay, so there's this other way that we figure out how strong something is, and that's called S character. If you remember, the sp3 was essentially saying there's an S and 3 P's, right? So out of these 4 letters, one of them is an S. Okay, so 1 out of 4 letters was an S. In other words, this has 25% S character. Cool. But over here, looking at this carbon and that carbon, there's an S and 2 P's for each carbon. Okay. This would be 1 out of 3 because there's one S out of every 3 letters. In other words, 33%. And then over here we had an S and a P, which would be 1 out of every 2 letters is an S, which would be 50%. Okay, so as you have more S character, you also have stronger bonds. Okay. And that's all this is showing right here. SP, SP2, SP3. As you have an SP, which is just 50% S character, it's going to be shorter, but it's going to have a lot of strength. Okay, I kind of wish they would reverse this, but I should have reversed it. All right, let's see what that means in terms of this. So again, triple bonds are stronger than double bonds, are stronger than single bonds, generally speaking. So here it said, which of the bonds shown in red is shorter, okay? Which would also be and stronger. And with more S character. All those things are related. Okay. So here we have a triple bond in red or double bond in red. I hope you agree that triple bond in red is going to be the stronger one. I need to put some paper back in. Here, I know you can't see that very well. Here, you have a single bond and a double bond. Hopefully you agree the double bond is shorter, stronger. It has more S character. Okay. This one's really good because here you have a single bond next to a double bond, and here you have a single bond next to a single bond. Let's go ahead and blow this sucker up. Let's talk about it. So I'm going to redraw it. So you have this carbon double bonded to an oxygen to a hydrogen, and you have this one with just a hydrogen and an OH. And the bond in question in each of these situations is this one and that one. Cool? I'm gonna pull back out a little bit. So I got room for my own hand in there. All right, so when you're in a situation like this, you want to look at kind of the carbons on either side. Remember that when I talk about a bond, I'm talking about something between this hydrogen and this thing, and this hydrogen and this thing. Okay, the hybridization of a hydrogen is always just going to be S, because there's only one thing on there. But this hybridization of this carbon, there's a double bond on it. Remember, there's a carbon right here. There's a double bond, a single, and a single. Do you remember its hybridization? Hopefully you remember it's sp2. Okay. I'll show you why. Go back. I'll show you why you should know that. When you have a carbon with a double bond, it's sp2. Okay, here we have a carbon right here, and it's got 1, 2, 3, 4 things on it. This is sp3. So even though these hydrogens are both just single bonded hydrogens, this one's close to an sp2, telling you it has more S character. And that's why that would be the shorter and stronger of the two. Okay, and that would be your answer. Okay. Now we move on to this one. Let's try this one, rank the bonds from shortest to longest. All right. So this one is not as fun as it looks. Let's talk about it. Boom, 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 boom. Those are all the carbons that are in here. Okay. And there are 1, 2, 3, 4 bonds we're supposed to rank. You might want to initially go, that's the shortest, then this, and then you won't know about those two, right? But here's how you really do each of these. You look at the S character in each of them, and you figure out the total amount of S character in that bond. So here we have a single bonded carbon right here. This would be sp3. I'm actually going to draw all the S in the P's. This one right here, you have double bond, would be sp2. This one here, sp2. This one right here, right, it only has two things, would be an sp. And this one right here would be an sp. Now, when we're talking about bonds, we're talking about the thing between them. We're not talking about one thing over here, one thing over here. We're talking about the thing that lies between them. I don't know why my focus is so off. Okay, there we go. Now you can see. So we're talking about the bond that's between them. So when I look at this bond, this whole bond is made up of 2 S's and 5 P's, right? So out of the total 7 things, 2 of them were S's. Now we move on to this next one. Out of the total 1, 2, 3, 4, 5, 6 things, 2 of them were S's. Out of the SPP and the SP, so 1, 2, 3, 4, 5. Here, 2 out of 5 were S's. And over here, out of our SP and SP, there's total 4, 1 out of 4 were S's. And now you look at these numbers and you say which one essentially is the largest, because that's going to be the one that's going to have the most S character. So 25% here, or excuse me, this was 2 out of 4, sorry, which should be 50%. And I was like, that really messed up. So sorry. 2 of them are S's out of the 4. So this one's 50%, for example. This one's 33%. This one, 2 out of 10, or 2 out of 5 would be 4 out of 10. That's 40%. Okay? So in case you can't see this, I didn't write it very well. This was 33%, right? So 2 out of 6 is a third. And this 2/7, I should probably know that fraction, but it's less, it's lower. It's less than the other ones. Okay? So this one is going to be our longest bond. This one right here, the one with less S character, because remember, shorter, stronger, more S character. But what you might not have expected was that the next shortest, or next longest, excuse me, is going to be this 33%, because if we're going to rank them in terms of numbers, this is 1, 2, 3, 4, right? Or 4, 3, 2, 1. In fact, that's what we get. As 33%, this one is the next shortest. Followed by, look at this sucker. It had 2 out of 5. Again, that's 4 out of 10, or in other words, 40% S character. This is 2 in terms of strength and shortest. And last but not least, we have this one, which is our number 1, which is kind of what we guessed. But you likely didn't guess that a double bond here would actually be longer than this single bond here. So looking at S character is really important in terms of determining exactly which one's going to be the stronger bond. So expect a question like that on your exam. In fact, I ask almost that exact same question. Whoa. My kids had a bunch of tape on the table. All right, moving on. Oh, polarity, we're almost done. Okay. So polarity, if this is our periodic table, we have something called increasing electronegativity. What electronegativity is that atom loves electrons, okay? So if you have an atom that has high electronegativity, the dude loves electrons. So yeah, let's do some examples. So let's say you have a carbon bonded to a fluorine. Fluorine is right here, carbon's right here. And hopefully you agree, based on this, fluorine is more electronegative. Now, when we talk about bonds, it's easy to forget that these bonds represent 2 electrons being shared between these 2 atoms. Okay, so these 2 electrons are being shared. It's lovely, and you think that they're all happy, but the truth of the matter is they're rarely shared equally. So this fluorine right here loves electrons more, meaning those 2 electrons kind of act like a magnet going toward the fluorine. And if you remember, fluorine has more protons, it's a positively charged thing, so or it has more positively charged stuff in the center, so it like sucks it in like a magnet. So it's attracting these 2 electrons toward it. Okay? So we usually draw an arrow to represent that toward the thing that those electrons are getting sucked toward. And we put a little positive charge over this end right here, representing that this side would be the positive and this side would be the negative, because this one's sucking electrons this way. Another way we would write that is a partial negative and a partial positive. This is lowercase delta, and it represents a partial charge. So even though carbon and fluorine looked like they were innocently sharing those electrons, the reality is fluorine actually takes on a lot more of the what we call electron density. These electrons go toward it, leaving this carbon positively charged, and you actually get like a little magnet. Okay? And this describes why things dissolve, etc. This was hopefully Gen Chem 1 stuff and a little bit of Gen Chem 2 stuff. But we should recognize that when stuff is bonded to something further over to the right and up, it's going to generally be electronegative. We would call this bond a polar bond. So if you have a polar bond, it's stuff that has unequal electronegativity in there. Okay, so based on that, I'm going to go ahead and rip this off so we can use it to solve this problem. Said, show the direction of the dipole in each arrow and label them with the partial positives and negatives. So here we have an HF. H is over here. Okay, it tends to be pretty darn positive. And fluorine is right here. So again, fluorine is the most electronegative element. We'll draw the dipole that way. This one would have the partial negative and this would have the partial positive. Boron is to the left of carbon, right there. So boron is less electronegative than carbon. Carbon is further to the right, so it's pulling the electrons toward it, leaving the positive charge over the boron. Carbon would have a partial negative, boron would have a partial positive, and that would be the answer to that question. Lithium. Lithium is over here. The first column right here, carbon's here, lithium's right there, all in the same row. So lithium is is less electronegative than carbon. Carbon's more electronegative. So we draw, again, the arrow toward the more electronegative thing, leaving the positive charge over the other side. So this one would be the partial positive, and this would be the partial negative. Okay, and last but not least, carbon here, chlorine here. Chlorine's over here. It's closer to fluorine. If you ever get stuck, just kind of count up and over, see which one's closer to the fluorine. Chlorine's directly under fluorine right here. It's more electronegative, so the dipole goes this way, leaving a positive charge over the carbon. This would be partial negative, and this would be partial positive. Now, carbon and hydrogen have a very special bond, as we've already discussed. Like when you draw them in skeletal structures, you don't even really draw them. But if you have something like this, propane, okay? Or I could draw it like this. Propane. If you have something like propane here, these carbons, first of all, the bonds between them are nonpolar, right? Because they're all carbon. So all these are nonpolar. Then when you look at the hydrogens, you want to be like, well, hydrogen's further over to the left, right? But the electronegativity between carbon and hydrogen is pretty similar. But not only that, if you have hydrogen down here pulling this carbon, you also have a hydrogen up here doing the opposite, or really I should say carbon's pulling the electrons away from each hydrogen equivalently. And so anytime you have something that's all carbons, it's always going to be nonpolar. Okay, there will be no overall dipole in that molecule, right? And this is why water, for example, if you remember, and you should know it now, there's 4 things on it. So this is tetrahedral. The oxygen here is sp3. Okay, so these things are pointed down like this, which is why I drew water this way instead of in the line. Water here is polar, because its overall dipole is going up like this. The oxygen is pulling from the hydrogen. This oxygen is pulling from that hydrogen. The molecule of water is polar. Most oils are hydrocarbons, meaning they're mostly made of hydrogen and carbon. So they're nonpolar. And that's why oils, when you pour olive oil or vegetable oil or something like that into water, they don't mix. Because this is polar and that's nonpolar, and polar requires other polar things to mix, and nonpolar requires other nonpolar things to mix. And that's why if you have an oil stain, you won't get it out with water. You need soap, and we'll talk about my cells at another time. All right, crew. That's all I'm gonna do. The rest of this is resonance, and I actually have a separate video for this, which I want you to watch instead of what I have here. Hopefully that helps. All right, have a good one.